Hello everyone, welcome to the Digital Electronics class. In this presentation, we will understand what is a D flip-flop and how we will make a D flip-flop by using a SR flip-flop. We already know what is a SR flip-flop. So we have drawn the truth table of the SR flip-flop as shown in this table. From the truth table of the SR flip-flop, we will derive the conclusion for D flip-flop. On observing the truth table for SR flip-flop, we see that if we want to store a 0, then we will have to give the inputs as S is equal to 0 and R is equal to 1. And if we want to store a 1, then we will have to give S is equal to 1 and R is equal to 0 as the inputs. That is, if S is equal to 0 and R is equal to 1, then a 0 will be stored in the SR flip-flop. Similarly, if S is equal to 1 and R is equal to 0, then a 1 will be stored in our SR flip-flop. Also, on observing this truth table, we see that the inputs S and R are always complement to each other. That is, when S is 0, R is 1, and when S is 1, R is 0. So, there is no need to give this S and R inputs individually. We can just give one input to this flip-flop and complement the other. That is what we have to do to get the D flip-flop. Now what about this case? That is, when the value of S is 1 and R is 1, we see that this is an invalid case. So we are not going to use this case. So if we want to store our data, then we can do so by using a D flip-flop as shown in this figure. From this figure we see that D is the data, and this is one of the most commonly used flip-flops, because in D flip-flop we just give the inputs, we store the data, and then we remove the clock, but our data will still be there. That is why D flip-flop is a very important flip-flop. So we see that we can convert a SR flip-flop to a D flip-flop by connecting an inverter from the S input to the R input, so that when the value of D is 0, the value of S will be 0 and the value of R will be equal to 1. Similarly, when the value of D is 1, the value of S will be equal to 1 and the value of R will be equal to 0. So we find that we only need a single input, that is D, to get the other input. We will just complement it. This is what we are doing here to obtain our D flip-flop by using the SR flip-flop. So we can make the D flip-flop like this. The entire circuit has been replaced by a single box, means this entire circuit is inside this box. Now let us find the truth table of this D flip-flop. We find that this is a very simple table in which we find that there is a single input D and there is a clock as the two inputs to this flip-flop, and Qn plus 1 is the output of this D flip-flop. Now if the clock is low, that is if the clock is 0, it means that this circuit will not take any input and the output will be the same as the previous input. That is, Qn is the output in this case. That is, in this case the value of Qn plus 1 will be Qn when the value of clock is low for any value of this D, we will get Qn as the output in this case. Now when the value of clock is high and the value of D is low, it means that S will be equal to 0 and R will be equal to 1. And from this table we find that when S is 0, R is 1, then the output Qn plus 1 is 0. So in this case, the value of Qn plus 1 will be 0. Now when the clock is high and the value of D is also high, it means that the value of S will be equal to 1 and R will be equal to 0. So from here we find that when the value of S is 1 and R is 0, then the output is Qn plus 1 is 1. So we will get a 1 here. Now the last case, that is S is equal to 1 and R is equal to 1, is not possible in D flip-flop because we have connected an inverter from the input S to R input. So we will not get this configuration, that is here we cannot have S is equal to 1 and R is equal to 1. So this is the truth table of D flip-flop. We see that this is a very simple truth table. So that's all in D flip-flop. Hope this topic is clear to all of you. See you in the next presentation.